Dear students, in this chapter Dual Nature of Matter, today let us discuss the topic Dual Nature of Electromagnetic Radiation and Dual Nature of Matter. Quantum theory was proposed by Max Planck. This theory gave birth to a new concept of dual nature of radiation. The radiation exhibits both particle and wave nature. In the phenomena like interference, diffraction, polarization, etc., the interaction takes place between the radiation and the radiation. Such phenomena are explained by considering wave nature for the radiation. To explain interference, diffraction, polarization, etc., wave nature is required. A radiation is considered as a wave. But in phenomena like photoelectric effect, Compton effect, the interaction is taking place between radiation and the particle. Such phenomena are explained by considering the particle nature for the radiation. Thus, the radiation behaves both as the particle and the wave. This is called dualism of electromagnetic radiation, or this is the dual nature of electromagnetic radiation. But the radiation, it cannot exhibit particle and wave nature simultaneously, because there is a contradiction in the properties of the wave and the particle. A wave is always characterized by its frequency, wavelength, amplitude and intensity. And the wave, it has got definite wavelength and it spreads out in the medium and it occupies a long region. But a particle, it is characterized by its mass, velocity, momentum, energy, and it occupies a definite point in space. Because of these differences in the properties of the radiation and the particle, it is very difficult to accept the dual nature for a radiation. How a radiation can have both these properties, even though the properties of the particle and the wave are entirely different. But however, in order to explain the experimentally observed facts, the two or the dual nature must be considered for the radiation, so it is accepted. See here, the radiation behaves like both particle and the wave, and radiation is part of one. Radiation is an entity of the nature. Nature is mainly classified into two groups as matter and energy. Energy nothing but radiation. These are the main branches or the parts of the nature, matter and radiation. If radiation has got dual nature, why can't matter can have this dual nature? Because nature is always symmetric, it is impartial. If radiation can have dual property, dual nature, then matter should also possess dual nature. This idea was suggested in 1924 by Victor de Broglie. According to him, electrons, protons, such particles which behave under certain conditions, these particles, they behave like wave train also. The wavelength of these waves depends on the momentum of the particle. This idea was immediately accepted. Later it was extended by Heisenberg, Schrödinger, Dirac, Max Born and others, and this one led to the foundation of a new branch called wave mechanics. And in wave mechanics, matter wave was taken into consideration. And what actually matter wave is? Matter wave or matter waves are the waves associated with a moving particle. Whenever a particle is in motion, it is associated with the waves called matter waves. And this hypothesis was proposed by de Broglie. So matter waves are also called as de Broglie waves. Now the expression for de Broglie wavelength or expression for wavelength of this matter waves, also called de Broglie wavelength. According to quantum theory, the energy carried by a photon is equal to h nu. H is Planck's constant, nu frequency of that photon. But energy is also, for a particle, energy is also given by mc square. That gives m as E by c square, but E is h nu, so that we get mass of the particle. Here we consider the photon, energy packet, photon. Mass of that photon is given by the formula h nu by c square, which is moving with the speed c. Then what is the momentum of the photon? Momentum is mass into velocity, mc, but m is E by c square, so that we get momentum p as E by c, but E, energy of the photon, is h nu, so that momentum is h nu by c, where the photon is moving with the velocity equal to velocity of light. That is, p is equal to h by c into nu, or nu, it is nothing but c by lambda. You know that c is equal to nu lambda, so nu is c by lambda, so that we get p as h by lambda. From this we get lambda as h by p. Here lambda is the wavelength of that matter wave given by h by p. Whenever a particle is moving with the whenever a particle is having the momentum mv, momentum p, that equal to mv, in that case wave length of the wave associated with that moving particle given by h by p. This was the expression given by de Broglie for the wavelength of the matter wave. Now de Broglie wavelength lambda, it can also be expressed in terms of energy. Whenever a particle is in motion, the particle possesses kinetic energy due to its velocity given by half mv square. Or if you rearrange that half mv square as half m square v square by m, and there m square v square becomes p square, so that we get E as p square by 2m. From this the expression for momentum becomes root 2me, so that lambda is h by square root of 2me. This is the expression for de Broglie wavelength in terms of energy. The expression for lambda de Broglie wavelength can also be written in terms of the absolute temperature. Suppose the particle is maintained at temperature say T, absolute temperature T, then its kinetic energy is given by 3 by 2 kT. If you substitute E as 3 by 2 kT, then we get lambda as h by square root of 3m kT, where k Boltzmann constant, T the absolute temperature. This is the expression for lambda in terms of temperature. Thus these are the expressions for lambda in terms of momentum, in terms of energy, and in terms of absolute temperature. Suppose the particle is an electron now. So let the particle be electron. M is the mass of the electron. Then if this electron, if it is accelerated by a potential say V, whenever an electron is accelerated in a potential field V, it acquires kinetic energy. The kinetic energy acquired by the electron is given by E into V, E charge of the electron, so that lambda becomes h by square root of 2m E. E is nothing but EV, so that the dependence of the de Broglie wavelength on potential is given by the formula lambda equal to h by square root of 2m EV. Neglecting the relativistic variation of mass, whenever electron is moving with a very high speed, there will be variation in its mass. If we neglect that relativistic variation in mass, then mass of the electron can be taken as m naught, the rest mass. M naught is rest mass of the electron, 9.1 into 10 power minus 31. E is the charge of the electron, 1.6 10 power minus 19. H Planck's constant. By substituting all these values, we get lambda as 12.27 angstrom by square root of V. Angstrom is 1 angstrom is 10 power minus 10 meter. So lambda comes out to be 12.27 angstrom, or 12.27 into 10 power minus 10 divided by root V. Root V, that much meter. This relation says that lambda varies with potential, inversely as square root of the potential. The de Broglie wavelength lambda is h by p, and one can observe this. One can observe the association of waves with a moving particle in case of microscopic particles only. In case of microscopic particle, we can observe this de Broglie wavelength whenever a particle is in motion. Is it possible to observe the de Broglie waves in case of macroscopic particles having large size or certain large sized bodies? Is it possible to observe these de Broglie waves in such macroscopic particles? So in case of macroscopic particles, say a marble or a cricket ball, let us consider a cricket ball or a ball, any ball of mass 1 gram moving with the velocity 1 centimeter per second, say. Then its momentum, if we calculate, it comes out to be 10 to the power minus 5 kg meter per second. If you calculate lambda, then lambda comes out to be 6.625 into 10 to the power minus 29. That 10 to the power minus 29 meter. It is so small that it is not at all possible to measure that wavelength. In order to measure wavelength, that wavelength should be in the order of atomic size, that is 10 to the power minus 10 meter. In such a case, only one can measure that wavelength. So in macroscopic bodies, since lambda is very, very small, it is not possible to measure the lambda, so that we can't observe the association of de Broglie waves with macroscopic particles in practice when they are in motion. We observe the de Broglie waves in case of microscopic particles only. The next topic is phase velocity and particle velocity. See, whenever a wave is produced, how actually a wave is produced? A wave is nothing but the disturbance produced in the medium. That wave is always produced due to the periodic vibrations of the particles of the medium, and that periodic vibration gets transferred from one particle to other particle, and the particles of the medium, they do not vibrate simultaneously, or they do not get displaced. Always a particle, when it begins its vibrations, it always begins its vibration a little later than the particle previous to it or its predecessor. Hence, there is always a phase change, a progressive phase change as we travel from one particle to the next particle in the medium. This progressive change in phase, it is observed in the form of the wave. And the velocity with which that wave travels in the medium is called the phase velocity or the wave velocity. Velocity with which a single wave travels through the medium is called wave velocity or phase velocity. The expression for phase velocity or the wave velocity is, let us consider a wave of wavelength lambda, frequency nu, let its velocity, let it be Vp, V suffix p, phase velocity, and it's given by nu lambda. We have the angular frequency omega given by 2 pi nu, therefore nu becomes omega by 2 pi. And the propagation constant, also called as wave number, denoted as k, propagation constant, defined as 2 pi by lambda. So lambda is 2 pi by k. Then in the expression Vp equal to nu lambda, if we substitute omega and k, we get Vp as omega by k. Omega is angular frequency, k is called propagation constant. So phase velocity expression is omega by k. So we have energy. So if you consider a particle, the energy is given by h nu, so that nu is E by h. Momentum of the particle is h by lambda. A material particle having energy, say moving with certain velocity, energy is h nu, nu is E by h, momentum is h by lambda, so that we get lambda as h by p. Then Vp omega by k, you substitute there, we get Vp as E by p. This relation Vp equal to E by p holds good in case of de Broglie waves associated with the moving particle. So for the de Broglie wave associated with the moving particle, the phase velocity is given by the formula E by p, where E is the energy. But energy, it's a particle is moving, along with that particle, along with the moving particle, a wave is associated. So energy of that particle can also be taken as mc square, where m is the mass. So that your Vp becomes mc square by p, means momentum mv, we get Vp as c square by v. In case of de Broglie wave due to the movement of the material particle, the phase velocity of that matter wave, we get it as c square by v, where v is velocity of that particle, vp velocity of the wave, v velocity of the particle, are connected as vp equal to c square by v. C is velocity of light in vacuum. Velocity of the particle cannot be equal to c. V is always very much less than c, so that vp equal to c square by c v. From this we get vp more than greater than c square. As v is very small compared to c, vp is more than c square. What the relation says, the velocity of the wave is greater than c square. But as per the theory of relativity, no particle can have, or the wave cannot travel the velocity more than the velocity of light. Not possible according to the theory of relativity. But here, if the particle velocity v is less than c, vp should be more than c. vpv, vp is velocity of the wave, v velocity of the particle. vp more than c, v less than c. What it implies? The wave travels very much faster than the particle. Whenever a particle is in motion associated with the wave, and the particle and that particular wave, they are not moving together. Instead, this relation says wave travels very much faster than the particle, leaving the particle behind. Particle is left back, the wave travels faster than the particle. But this is not possible. Particle at one point, wave somewhere else, but this is not possible. So, in case of matter waves, this idea of single wave was discarded. Instead, a moving particle is not considered as a single wave. A moving particle cannot be equivalent to a single wave. Instead, it is considered to be equivalent to a group of waves. It is the wave associated with the moving particle is considered as the group of waves. It's equivalent to a group of waves. And here the particle and the group of waves, they travel together, so that the velocity of that group of waves, called the group velocity, velocity of the group of waves, that group of waves is a packet of wave, also called wave packet. It's a packet of many waves having different frequencies, different wavelengths, different velocities, but it is considered as a single packet traveling with a certain velocity called the group velocity. The group travels with a definite velocity. That group velocity is always equal to the particle velocity. So group velocity is nothing but a group consisting of a number of waves of different frequencies superimposed upon each other. Then the velocity with which this slowly varying envelope of the modulated pattern due to group of waves travels in a medium is known as group velocity. Group of waves or the wave packet, example is white light. White light travels as a single wave, but actually it is a combination of seven waves of different frequencies or different wavelengths. It is a combination of 7 wavelengths. We can treat it as a group wave or a wave packet having a single velocity, nothing but velocity of light. Thus, the matter waves are considered as the group waves or wave packets. Now, let us find out the expression for group velocity. Velocity of this group of waves. Group of waves consisting of many number of waves superposed on each other to give a single wave as a group or a packet. Here, let us consider the group consisting of only 2 waves of displacements y1 and y2. Let omega1, omega2 be the angular frequencies of those 2 waves. K1, K2 be the propagation constants. And here, let the omega1 minus omega2, let it be small, let it be delta omega. K1 minus K2 is taken as delta K. Suppose these 2 waves superimpose on each other. They fall on each other, they are combined to form a single wave group or a wave packet. Let Vg represent the group velocity of this wave packet. Then when these 2 waves are superposed, resultant will be y is equal to y1 plus y2. Resultant displacement is y1 plus y2. Then we add those two equations, y equal to a cos omega 1t minus k1x plus a cos omega 2t minus k2x. You simplify this. This of the form a common, cos a plus cos b. So the form cos a plus cos b. Cos a plus cos b expanded as 2 cos a plus b by 2 cos a minus b by 2. Apply this formula and expand and simplify. You get the expression y equal to 2a cos omega t minus kx into cos delta omega t by 2 minus delta kx by 2. Here omega is nothing but omega 1 plus omega 2 by 2. K is nothing but k1 plus k2 by 2. Delta omega is omega 1 minus omega 2. Delta k is k1 minus k2. See here, the resultant wave, the resultant expression y, it consists of two parts. Here 2a cos delta omega t by 2 minus delta kx by 2. This part is nothing but the amplitude, and cos omega t minus kx gives the phase velocity of the wave. This part gives the phase velocity of the wave. So here amplitude is variable 1, so that the second part is the modulated form. It represents the group of wave having different frequencies, and here cos omega t minus kx. From this we get the phase velocity Vp, wave velocity. Phase is nothing but wave velocity Vp as omega by k, and from the other part cos delta omega t by 2 minus delta kx by 2. From this we get the group velocity as delta omega by delta k. So the group velocity is delta omega by delta k. Delta omega delta k are very small, then Vg can be taken as d omega by dk. That is differentiation of omega is 2 pi nu by differentiation of or variation in 2 pi by lambda. From that we get Vg as minus lambda square d nu by d lambda. Differentiation of nu is d nu. Differentiation of 1 by lambda is minus 1 by lambda square d lambda. So we get Vg as minus lambda square d nu by d lambda. This is the expression for the group velocity of the group wave or a wave packet. Now let us find out the relation between group velocity and phase velocity. How Vg and Vp are connected. What's the relationship between them? For this, again we consider the wave velocity or the phase velocity as Vp omega by k, group velocity defined as d omega by dk. Now substitute k as 2 pi by lambda, omega as 2 pi nu. Then from equation 1, differentiate. See the wave number, you get wave number k equal to 2 pi by lambda. Now differentiate k equal to 2 pi by lambda with respect to lambda, so that left hand side becomes dk by d lambda equal to minus 2 pi by lambda square. 2 pi constant, differentiation of lambda is minus 1 by lambda square. So dk by d lambda we get 2 pi minus 2 pi by lambda square. And omega is 2 pi nu, that is 2 pi into nu is v by lambda. V is Vp, Vp by lambda. Again differentiate this omega with respect to lambda, that is d omega by d lambda. Differentiate expression 2 pi Vp by lambda with respect to lambda. We get left hand side d omega by d lambda, right hand side Vp and lambda both are variables. Vp lambda variables, differentiate. 2 pi common, keep Vp constant, differentiation of lambda is minus 1 by lambda square plus keep 1 by lambda dVp by d lambda. Differentiation of Vp with respect to lambda is dVp by d lambda. So that we get the expression d omega by d lambda as minus 2 pi by lambda square into Vp minus lambda dVp by d lambda. See here in the first term minus Vp by lambda square, 1 by lambda square common, we keep it outside. So in the second term 1 lambda comes in the numerator. This is d omega by d lambda, equation 4. Now consider 4 by 3. 4 by 3 gives d omega by dk. Right hand side you get Vp minus lambda dVp by d lambda, or d omega by dk nothing but Vg, group velocity. Thus group velocity equal to Vp minus lambda into dVp by d lambda. This is the expression for group velocity in terms of phase velocity or wave velocity. Now show that group velocity is equal to particle velocity. As I told, the matter waves that travel in the form of group of waves or the wave packet, the velocity of that group of waves, it is Vg, is always same as the particle velocity. Now to show this, Vg equal to V, let us consider the group velocity Vg. Definition is d omega by dk. Here we have a particle of mass m moving with the velocity v. Then energy possessed by that particle is mc square, its momentum is mv. If m0 is the rest mass of that particle, that rest mass is given by m equal to rest mass and the relativistic mass are connected as m equal to m0 by root 1 minus v square by c square. So momentum p equal to mv becomes p equal to m0 v by root 1 minus v square by c square. Energy of the photon is h nu, E is mc square, so h nu equal to mc square. From this we get nu as mc square by h. What is m? m0 by root 1 minus v square by c square. Substitute m in terms of rest mass. So you get m0 c square by h into root 1 minus v square by c square. That is nu. Angular frequency is 2 pi nu. Therefore omega becomes 2 pi into nu. It is m0 c square by h root 1 minus v square by c square. This is omega. Now let us differentiate omega with respect to omega with respect to v, that is d omega by dv. D omega by dv is, see here in the equation, 2 pi m0 c square by h, constant, keep it outside. Then we have the term root 1 minus v square by c square in the denominator, take it to the numerator, becomes 1 minus v square by c square power minus half. Now when you differentiate omega with respect to t, d omega by dv with respect to v, d omega by dv, what we get is 2 pi m0 c square h, constant, outside. Then differentiate 1 minus v square by c square power minus half. It becomes minus half into 1 minus v square by c square power minus 3 by 2 into differentiation of minus v square by c square. Differentiation of minus v square by c square. It is minus 2v by c square. C square constant there. Differentiate v square. It is 2v dv. And you simplify, see here, c square gets cancelled, 2 gets cancelled, minus minus becomes plus, so that d omega by dv becomes 2 pi m0 by h into 1 minus v square by c square power minus 3 by 2 into v into dv. Let the equation be 1. Now let us consider the expression for lambda. Lambda is h by p. P is mv. So h by mv. M is m0 by root 1 minus v square by c square. So that lambda is h by m0 v, that root 1 minus v square by c square goes to the numerator, becomes 1 minus v square by c square power half. So it's the denominator there itself, in that position it is minus half, goes to the numerator, becomes plus half. So lambda is h into 1 minus v square by c square power half by m0 v. This is lambda. Now define k, propagation constant, 2 pi by lambda. That is k equal to 2 pi by, substitute lambda and simplify. You get k as 2 pi m0 v by h into 1 minus v square by c square power half. Take that 1 minus v square by c square power half to the numerator, becomes minus half. Now differentiate k with respect to v. differentiate k with respect to v. Left hand side dk by dv, and right hand side 2 pi m naught by h common, keep it outside, and differentiate the first term, that is 1 minus v square by c square to the power minus half. Differentiate that, it becomes minus half into 1 minus v square by c square power minus 3 by 2 into minus 2v dv by c square plus 1 minus v square by c square to the power minus half. As it is differentiation of v, it is dv, and you simplify, then there you get 2 pi m naught dv by h outside the bracket. Inside we have the first term is v square by c square into 1 minus v square by c square power minus 3 by 2 plus the next term is 1 minus v square by c square power minus half. Here take 1 minus v square by c square minus 3 by 2 common outside the bracket. So inside you get v square by c square plus 1 minus v square by c square. From that v square by c square minus v square by c square 0. So you get dk by dv as 2 pi m naught dv by h into 1 minus v square by c square power minus 3 by 2. Let the equation be 2. Now consider equations 1 and 2. 1 divided by 2 gives left hand side 1 by 2 is d omega by dk by d omega by dv by dk by dv. Get d omega by dk. What is d omega by dk? Group velocity vg. And in the right hand side, if you divide the right hand side terms, then all the terms cancel, only v remains, so that we get vg is equal to v. This indicates that group velocity is equal to particle velocity. Means in case of de Broglie waves, in case of matter waves, the velocity of the particle is same as the velocity of the wave, but their wave is not a single wave, but it's a group of waves. It's a group of waves or a wave packet, and that whole group of waves, combination of many waves of different frequencies, different amplitudes, but it travels as a single wave called group of waves with a velocity equal to the particle velocity. This is how the movement of the particle and the wave together is explained by using the idea of group velocity in matter waves. With this, I conclude.